Today we are going to study the magnetic effect of electric currents. So the discovery of magnetic effect was quite accidentally in 1820. A Dutch scientist, Hans Christian Ørsted, discovered accidentally the magnetic effect of electric currents. So one day, in a classroom demonstration by passing electric current through a conducting wire, unexpectedly there is a compass needle which is kept just below of this conductor. He noticed that the magnetic needle shows a small deflection. So what is a compass needle? A compass needle is nothing but it is a very small magnet which is also a pivoted one. If a magnet is deflected only when in presence of another magnet, unexpectedly here there is no magnet, here there is only a conducting wire, a current carrying wire is here, and he noticed that a pivoted compass needle which is kept just below of this conducting wire, and this needle which exhibited a small deflection. And he finally concluded that this current carrying conductor, but it is nothing but it is the flow of electric charges through a conductor. So when a charge is flowing through a conductor, that will produce an electric current. And this moving charge which produces a magnetic field in a region around it. That means around this current carrying conductor there is a magnetic field. This is because here there is no electric field. This is because the electric charges, means the electrons and the positively charged ions are present in this conductor, and the presence of both positive and negative charges will neutralize the electric field. That means he finally concluded that a moving charge which produce, that means an accelerated moving charge which produce a magnetic field. And the presence of this magnetic field is detected only with the help of the deflection of this compass needle. Magnetic effect of electric currentനെ കുറിച്ച് ആദ്യമായി മനസ്സിലാക്കി തന്നത് 1820 ഡച്ച് സയൻറ്റിസ്റ്റായ ഹാൻസ് ക്രിസ്റ്റ്യൻ ഏഴ്സ്റ്റഡ് ആണ്. ഒരു ദിവസം അദ്ദേഹം രാവിലെ ക്ലാസ്സിൽ ഒരു കറണ്ടിനെ കുറിച്ചൊരു എക്സ്പെരിമെൻ്റ് കണ്ടക്ട് ചെയ്ത സമയത്ത് ഈ കറണ്ട് കടന്നുപോയ കണ്ടക്ടറിൻ്റെ തൊട്ട് താഴ്വശത്തിരുന്ന ഒരു കോമ്പസ് നീഡിൽ എന്ന് പറയുമ്പോഴൊരു കാന്തസൂചിയാണ്, ഒരു പിവറ്റ്, അതിൻ്റെ വെർട്ടിക്കൽ ആക്സിസിലൂടെ റൊട്ടേറ്റ് ചെയ്യുന്ന, ഫ്രീ ആയിട്ട് റൊട്ടേറ്റ് ചെയ്യുന്ന ഈ ഒരു നീഡിൽ ഡിഫ്ലക്റ്റ് ചെയ്യുന്നതായിട്ട് അദ്ദേഹം മനസ്സിലാക്കി, അല്ലെങ്കിൽ അദ്ദേഹം കണ്ടു. എപ്പോഴെങ്കിലും ഒരു മാഗ്നറ്റിക് നീഡിൽ ഡിഫ്ലക്റ്റ് ചെയ്യണമെങ്കിൽ അതിന് സമീപത്തൊരു മാഗ്നറ്റിക് ഫീൽഡ് ഉണ്ടാകണം, അല്ലെങ്കിൽ ഒരു മാഗ്നറ്റ് വേണം. ഇവിടെ ഒരു മാഗ്നറ്റ് ഇല്ല, അതിന് പകരം ഇവിടെ കറണ്ട് കടന്നു പോകുന്ന ഒരു കണ്ടക്ടർ മാത്രമേ ഉള്ളൂ. ഇതിനകത്തൂടെ കടന്നു പോകുന്നതാണ് ഇലക്ട്രോണുകളാണ്, ഇലക്ട്രോണിൻ്റെ മോഷനാണ്, ഈ കണ്ടക്ടറിലൂടെ പാസ് ചെയ്യുന്ന ഇലക്ട്രോൺസ് ആണ്. ഇലക്ട്രോണിൻ്റെ വേക്കൻറ്റ് പ്ലേസ് വരുമ്പോഴത്തേക്കും ഇവിടെ പോസിറ്റീവ് അയോൺസ് വരും. അപ്പോൾ ചുരുക്കി പറഞ്ഞാൽ നമുക്ക് മനസ്സിലാകുന്നത് ഈ ഒരു കണ്ടക്ടറിൽ ഇലക്ട്രിസിറ്റിയെ കൊണ്ടുപോകുന്ന ഇലക്ട്രോണുകളും അതിൻ്റെ വേക്കൻറ്റ് പ്ലേസിൽ വരുന്ന പോസിറ്റീവ് അയോണിൻ്റെ എണ്ണം ഈക്വൽ ആയതുകൊണ്ട് അവിടെ ഇലക്ട്രിക് ഫീൽഡ് ഉണ്ടാകാനുള്ള സാധ്യതയില്ല. പിന്നുണ്ടാകുന്നത് ഈ ഒരു ആക്സിലറേറ്റഡ് ചാർജസ് അല്ലെങ്കിൽ ഇലക്ട്രോണുകൾ അവിടെ ഒരു മാഗ്നറ്റിക് ഫീൽഡ് പ്രൊഡ്യൂസ് ചെയ്യും എന്ന് അദ്ദേഹം മനസ്സിലാക്കുകയും അങ്ങനെ 1820 ഈ മാഗ്നറ്റിക് ഇഫക്റ്റ്, ഇലക്ട്രിക് കറണ്ടിൻ്റെ മാഗ്നറ്റിക് ഇഫക്റ്റിനെ കുറിച്ച് അദ്ദേഹം ഡീറ്റെയിൽ ആയിട്ട് ഈ ഒരു എക്സ്പെരിമെൻറ്റിലൂടെ നമുക്ക് പറഞ്ഞു തരികയും ചെയ്തു. Experimental inferences of Ørsted experiment. The first inference of this experiment is the non-magnetic elements such as gold, silver, copper, aluminum, etc. also exhibited the same phenomena, the magnetic effect of electric currents. In addition to the metals such as iron, cobalt, nickel, the another non-magnetic elements such as the gold, silver, aluminum, etc. also exhibited the same process, the magnetic effect of electric current exhibiting by those elements. That is the first experimental result. Non-magnetic elements such as gold, silver, aluminum, copper, etc. shows the same phenomena. Okay, the second one, a charge which is in a state of rest, such a charge is called static charge. The static charge can produce only an electric field. Electric field means it is a region in space where the influence of the charge is detected. That is called electric field. A charge which is in uniform motion, which produces only magnetic field. But in the case of an accelerated charge, a charge which is moving with a non-uniform velocity, that charge is called an accelerated charge. The accelerated charge which produces both electric and magnetic field. It's a very important thing. A charge which is in a state of rest which produces only an electric field. A charge which is in uniform motion produces only magnetic field. But in the case of an accelerated charge which produces both electric and magnetic field. So that is another experimental inference. And the third one, the direction and the geometry of the magnetic field which depends on the shape of the conductor. In the case of a straight conductor which produces a concentric circular magnetic field. But in the case of a circular conductor which produces a magnetic field acts along the axis of the circular conductor. That means the shape of the magnetic field which depends on the geometry of the conductor. If the given conductor is a straight one, the magnetic field is circular. But the given conductor is circular, the magnetic field is a straight line. So these are the major inferences detected by Christian Easted in his experiments. Is it clear? ഒരു കാര്യം നമ്മൾ മനസ്സിലാക്കുന്നത്, നമുക്ക് തന്നിരിക്കുന്ന അല്ലെങ്കിൽ ഈ ഈസ്റ്റഡിൻ്റെ എക്സ്പെരിമെൻറ്റിൽ നിന്നും നമ്മൾ മനസ്സിലാക്കിയ 2-3 കാര്യങ്ങളുണ്ട്. ഒന്ന്, നമുക്ക് തന്നിരിക്കുന്ന എലമെൻറ്റ് നോൺ മാഗ്നറ്റിക് ആണെങ്കിൽ പോലും, ഇപ്പോൾ സിൽവർ പോലുള്ള, സ്വർണം പോലുള്ള, വെള്ളി പോലുള്ള എലമെൻ്റ് ആണെങ്കിലും ഇത് മാഗ്നറ്റിക് ഇഫക്റ്റ് കാണിക്കും എന്നാണ് ഇദ്ദേഹം മനസ്സിലാക്കിയത്. അതിപ്പം ഇരുമ്പ് വേണമെന്നില്ല, അല്ലെങ്കിൽ അയൺ വേണമെന്നില്ല, അല്ലെങ്കിൽ കൊബാൾട്ട് വേണമെന്നില്ല, നിക്കൽ വേണമെന്നില്ല. നിക്കൽ കാണിക്കുന്നത് പോലെ, കൊബാൾട്ട് കാണിക്കുന്ന പോലെ, അയൺ കാണിക്കുന്ന പോലെ മാഗ്നറ്റിക് ഇഫക്റ്റ് ഗോൾഡും സിൽവറും കോപ്പറും അലൂമിനിയവും കാണിക്കും. അതുപോലെ നമ്മൾ മനസ്സിലാക്കുന്ന മറ്റൊരു കാര്യം, നമുക്ക് തന്നിരിക്കുന്ന ഇലക്ട്രിക് ചാർജ് സ്റ്റാറ്റിക് സ്റ്റേറ്റിലാണെങ്കിൽ, നിശ്ചലാവസ്ഥയിലാണെങ്കിൽ അതിനു ചുറ്റും ഒരു ഇലക്ട്രിക് ഫീൽഡാണ് ഡെവലപ്പ് ചെയ്യുന്നത്. നമുക്ക് തന്നിരിക്കുന്ന ചാർജ് യൂണിഫോം സ്പീഡിലാണ് സഞ്ചരിക്കുന്നതെങ്കിൽ അത് മാഗ്നറ്റിക് ഫീൽഡ് പ്രൊഡ്യൂസ് ചെയ്യും. തന്നിരിക്കുന്ന ചാർജ് ആക്സിലറേറ്റഡ് ആയിട്ടുള്ള മോഷനാണ് എക്സിബിറ്റ് ചെയ്യുന്നതെങ്കിൽ ഈ 2 ഫീൽഡും കാണിക്കും, ഇലക്ട്രിക് ഫീൽഡും കാണിക്കും, മാഗ്നറ്റിക് ഫീൽഡും കാണിക്കും. സോ നെക്സ്റ്റ് വൺ we discuss about Biot and Sawad law. And according to this law, the magnetic field produced by a current carrying element, for example, this is a conducting wire. Let us imagine I ampere current passing through this conductor, and we should take a small element of this conductor. Say AB is a small element of length dl. And how much field intensity produced by this current element at any point P placed at a distance R from this element. We have to find the magnetic field intensity at any point P placed at a distance R from this current element. And this magnetic field was experimentally determined by Biot and Sawad. It is actually pronounced as Biot and Sawad. That is the correct pronunciation. The Biot can be pronounced by Biot and Sawad can be pronounced by Sava. And these 2 persons was experimentally demonstrated the magnetic field intensity at any point placed at a distance r from this current carrying conductor. And according to them, the magnetic field intensity at any point P due to this element of length dl is given by the magnetic field intensity is directly proportional to the strength of the electric current. Here I is the intensity of electric current passing through this conductor. The magnetic field at this point is directly proportional to the strength of the current carried by this element. The second factor is the magnetic field intensity at this point is also directly proportional to the length of this element. The element is very small, the intensity is also small. That means the intensity at any point P due to this element is directly proportional to the length of the element dl, and also directly proportional to sine of the angle between the direction of electric current and the line joining from the element to the point P. And this is the direction of electric current. Here we noticed that the arrow mark which simply shows the direction of electric current through this conductor, and this is the line joining from this element to the point P, and this is the angle between the direction of electric current I and the line from the midpoint of the element to the point P. Here theta which shows the direction, the angle between them, and according to this rule, the magnetic field intensity at any point P is given by dB, it's a vector quantity, and this magnetic field is directly proportional to the first factor is the strength of the electric current, then second one the length of the elements, and third factor the sine of the angle between the direction of electric current and the line joining from the midpoint of this element to the point P. And here another important factor is the magnetic field intensity at this point is inversely proportional to the square of the distance between the point P and the element, the midpoint of the element AB. So they connected all the four factors, and this equation can be denoted by dB proportional to I dl sin theta by r square. Here I is the strength of or the intensity of electric current passing through this conductor, dl means the length of the element, then sin theta means the sine of the angle between the direction of electric current and the line joining from the midpoint of the element to the point P, and inversely proportional to square of the distance between the point P and the midpoint of this element. Then dB is equal to a constant. Here it is represented by mu 0 by 4 pi into ideal sin theta by r square, and here the term I and dl are connected together, and this ideal term is combined and it will be known as current element. This ideal term is called current element. It is the combined product of a vector and a scalar. Here I is the electric current, and dl means the length of the element which simply shows a particular direction. Therefore dl is a vector quantity and electric current is a scalar quantity, and this is the product of a scalar and a vector, and this combined term is called current element. And here we can simply say that the magnetic field intensity at any point P due to this current carrying conductor is given by ideal sin theta by r square, where ideal is a term which is called current element. It is the product of a scalar quantity and a vector quantity, and here theta is the angle between the direction of electric current and the line joining from the midpoint of the element AB and the point P, and inversely proportional to the square of the distance between the point and the element. And dB is equal to this proportionality constant is replaced by a constant, and that constant is here mu 0 by 4 pi, where mu 0 is a constant which is called permeability of the medium. Mu 0 is a constant is called permeability of the medium or free space. Here the medium is free space. Therefore, the value of mu 0 is equal to the value of mu 0 is equal to 4 pi into 10 raised to minus 7 Henry per meter. That is the value of mu 0 or permeability of free space. 4 pi into 10 raised to minus 7 Henry per meter. Therefore, now this equation becomes dB is equal to 4 pi into 10 raised to minus 7 by 4 pi ideal. Here dl is a vector quantity. Therefore, it becomes ideal sin theta by r square. Therefore, finally we get dB is equal to 10 raised to minus 7 ideal sin theta by r square. This is the final equation of this Biot and Sawad law or rule. This is the final equation. So, Biot and Sawad mathematically demonstrated the intensity of electric field at any point P due to a current element AB. The length of the element is here represented by dl, and the magnitude of the electric current is represented by I, and theta is the angle between the direction of electric current and the line joining from the midpoint C of this element to the point P, and R is the separation between the element and the point P. And according to them, the magnetic field intensity at P is given by dB, and dB is proportional to ideal. The first factor ideal is the product of a scalar and a vector quantity, and the combined term is called the current element, and it is directly proportional to the current element, and sine of the angle between the direction of electric current and the line joining from the midpoint C of the element to the point P, that is represented by sin theta, and inversely proportional to the square of the distance. And dB is equal to a constant into mu 0 by 4 pi into ideal sin theta by r square. Here mu 0 is a constant which is called permeability of free space, and the value of mu 0 is 4 pi into 10 raised to minus 7 Henry per meter, and therefore finally we get dB is equal to 10 raised to minus 7 ideal sin theta by r square. We have to study some applications of the Biot and Sawad rule. Here there are two important applications are given. So one is to find the magnetic field intensity, to find the magnetic field intensity produced by a current carrying conductor. Carrying conductor of infinite or infinite long. So this is one of the important application of Biot and Sawad rule. We have to find the magnetic field intensity produced by a current carrying conductor of infinite long or infinite length. For example, here there is a straight conductor of infinite long, but we have a limitation. We always draw a conductor of finite length because it is a finite region. So here xy is a straight conductor which carries a current of I ampere. The direction of electric current is as shown in figure. Then let us imagine a point P at a distance A from the midpoint of this straight conductor, and our experimental aim is to determine the magnetic field intensity at P due to this straight conductor of infinite long. Therefore, we imagine a small element AB of length dl. By using Biot and Sawad rule, first of all, or initially imagine a small element of length dl which carries the same ampere of current, and let's see is the midpoint of this element, and R is the separation between C and P. And using the above law, Biot and Sawad rule, the magnetic flux density at P due to this element AB of length dl is given by dB, and it is represented by dB. dB is equal to mu 0 by 4 pi into ideal sin theta by r square. We already learned this equation, and using Biot and Sawad rule, the magnetic flux density at P due to the small element of length dl is given by dB, which is equal to mu 0 by 4 pi into ideal sin theta by r square. And here mu 0 is a constant which is called the permeability of free space, and also we know the value of mu 0, which is equal to 4 pi into 10 raised to minus 7. And ideal is actually the product of a scalar and a vector quantity, and that quantity is together known as current element. And also we know that sin theta, sine of the angle between the direction of electric current and the line joining from the midpoint of the element to the point P, and R is the separation between the element and the point. Okay, then drawing two other lines from the extreme points of these elements, and let us imagine these lines can also have the same length R, almost the same length R. And here we imagine a small triangle ABD. For example, here AD is a line which is perpendicular to PB. This is because we have to remove a term ideal sin theta from this equation, and now this equation should be taken as equation number 1. The first aim to remove this ideal sin theta from this equation. So we imagine a small triangle ABD. A small triangle ABD, and we know that let theta is the angle between the direction of electric current and the line joining from the extreme point to the point P. So using this triangle, we can easily to find out the value of sin theta. So using this triangle, we know that sin theta is equal to opposite side by hypotenuse. Here opposite side is AD. The opposite side of this angle theta, that is AD, and hypotenuse AB, then AB which is equal to dl. The distance between A and B is the length of this element. So instead of writing AB, we have to write dl. So that is sin theta is equal to AD by dl. Therefore AD is equal to dl sin theta. That is another expression which is equal to the second one, question number 2. AD is equal to dl sin theta. Then here angle APB can be taken as phi, it's a small angle, or d phi. Angle APB can be taken as d phi, and we know that let P is a point which is the center, and AP or PA is another line. The length of this line is R, and drawing an arc by using this point P, means the midpoint P, and the length of the element PA, we can easily to draw an arc AD. Then according to some rule, means angle rule, angle is equal to arc by radius. Angle is equal to arc by radius. Here angle is d phi, and arc here AD, and radius is R. The separation between P and A, that should be taken as the radius of this arc. So it can be written as AD is equal to R into d phi. That should be taken as the next equation 3. That means our aim is to remove ideal sin theta from equation number 1. So we have to derive another two equations. One is AD is equal to dl sin theta, another AD is equal to R d phi. And combined these two equations, 2 and 3, we know that the left hand side of these two equations are equal. Therefore we can equating the right hand side, we get dl sin theta is equal to R into d phi. So So the value of dl sine theta is replaced by r into d phi. Now equation 1 becomes dB is equal to mu 0 by 4 pi r square into mu 0 I by 4 pi r square into r into d phi. So it becomes dB is equal to mu 0 I by 4 pi r into d phi. So using this figure, we have to say that using the triangle LPA, angle LPA is equal to phi. So the cosine of this angle, cos phi, is equal to adjacent side by hypotenuse. So it becomes A by R. Cos phi is equal to A by R, and therefore R becomes A by cos phi. So this is equation number 4, and this one is equation number 5. And here the R is replaced by A by cos phi, so it becomes, the above equation becomes dB is equal to mu 0 I by 4 pi into, R is replaced by A by cos phi, so it becomes A by cos phi. Cos phi goes to the numerator, so it becomes cos phi into d phi. And this is the magnetic flux at P due to the small element AB of length dl carrying a current of I ampere. But in actual practice, we have to find out the total flux at P due to the whole conductor xy. So that is obtained by integrating this expression between the limiting values of phi is equal to minus phi 1 and phi is equal to plus phi 2. That is a way for calculating the total flux at P due to the whole conductor. So now it becomes integral dB, it becomes B is equal to mu 0 I by 4 pi A into integral minus phi 1 to plus phi 2 cos phi into d phi. Here minus phi 1 is the limiting value of phi at the lower side, and phi 2 is the limiting value of phi at the upper side. So it becomes 4 mu 0 I by 4 pi A into integral minus phi 1 to plus phi 2 cos phi into d phi. And integrating this expression, you get mu 0 I by 4 pi A into integral cos phi into d phi is equal to sin phi, because integration is the inverse result of differentiation. So you get sin phi and giving the limiting values minus phi 1 to plus phi 2. Then how can you give the limiting values to this equation? So it becomes B is equal to mu 0 I divided by 4 pi A into, first of all, the upper limit is given to this equation. So now it becomes sin phi 2 minus sin minus phi 1. So this is a way for removing the limiting values, giving the upper limit and lower limit and take the difference. So it becomes mu 0 I by 4 pi A into sin phi 1 minus of minus phi 1. It becomes sin phi 1 plus sin phi 2. So this is the exact value of the magnetic flux at P due to the whole conductor xy. And this is the final equation. B is equal to mu 0 I by 4 pi A into sin phi 1 plus sin phi 2. But our aim is to determine the magnetic field intensity produced by a current carrying conductor of infinite length. Here it is a conductor of finite length. Let us imagine the conductor can have infinite length. The angle phi 1 becomes 90 degree, and at the same time the angle phi 2 becomes 90 degree. This is because the line joining from P to the extreme ends are usually parallel to each other. So the final equation becomes B is equal to mu 0 I divided by 4 pi A into sin 90. Phi 1 becomes 90. So sin 90 plus sin 90. Value of sin 90 is 1. So our equation becomes mu 0 by 4 pi into 2I by A. This is the final expression. Otherwise it becomes B is equal to mu 0 by 2 pi into I by A. Or it becomes B is equal to mu 0 I by 2 pi A is the final result. But this is the best equation because we know that the value of mu 0 by 4 pi is 10 raised to minus 7. Maybe it becomes 10 raised to minus 7 into 2I by A, and this equation can be used to find the exact value very easily. So you just remember this equation also, mu 0 by 4 pi into 2I by A, otherwise it becomes mu 0 I by 2 pi A. This is the final equation of the magnetic field intensity at any point P due to a conductor of infinite long. So here there is an exceptional case. If the point P is at one end of this conducting wire XY, for example this is a conductor XY of finite length, and here P is a point at one side of this conductor. Now let us imagine this conductor can have infinite length. Then the point P is at one side. The angle phi 1 becomes 90 and the angle phi 2 becomes 180 because this is a reference line. So your equation becomes B is equal to mu 0 I by 4 pi A into, now sin phi 1 becomes sin 90 and sin phi 2 becomes sin 180. So you get B is equal to mu 0 I by 4 pi A. So this is an exceptional case. Sometimes we have to find the magnetic field intensity at one side of this conducting wire. So നിങ്ങളൊരു കാര്യം മനസ്സിലാക്കാനുള്ളത്, നമ്മളിപ്പോൾ ഈ ഇൻഫിനിറ്റ് ലെന്തുള്ള കണ്ടക്റ്റിംഗ് വയറിൻ്റെ മാഗ്നറ്റിക് ഫ്ലക്സ് ആണ് കാണുന്നതെങ്കിൽ ഈ പോയിന്റ് പി അതിൻ്റെ മിഡിൽ പോയിന്റിലാണ് മറ്റേ ഇൻഫിനിറ്റിലേക്ക് എക്സ്റ്റെൻഡ് ചെയ്ത് പോകുന്നുവെങ്കിൽ നമ്മൾ പിയിൽ നിന്ന് ആ ഇൻഫിനിറ്റ് എൻഡിലേക്ക് വരയ്ക്കുന്ന phi 1 phi 2 ആംഗിൾ എക്സാക്ട്ലി 90 ഡിഗ്രി വരുന്നത് കൊണ്ട് സൈൻ phi 1 എന്നുള്ളത് സൈൻ 90 നമുക്ക് എഴുതാൻ പറ്റും, സൈൻ phi 2 എന്നുള്ളതും സൈൻ 90 എന്ന് എഴുതാം. സൈൻ 90യുടെ വാല്യൂ 1 വീതം ആയതുകൊണ്ട് ആണ് നമുക്ക് ഈ ഫോർമാറ്റ് വരുന്നത്, mu 0 by 4 pi into 2I by A. ഇതാണ് നമുക്ക് ഈ കാൽക്കുലേഷൻസ് വരുമ്പോൾ പ്രോബ്ലം സോൾവ് ചെയ്യേണ്ട കേസിൽ ഈ ഫോർമുല പഠിച്ചു വെച്ചിരിക്കുന്നതായിരിക്കും നിങ്ങൾക്ക് എളുപ്പം. കാരണം mu 0 by 4 piയുടെ വാല്യൂ ഡയറക്റ്റ് നിങ്ങൾക്ക് 10 raised to minus 7 എന്ന് എഴുതാൻ പറ്റും. സോ 10 raised to minus 7 into 2I by A എന്ന് എഴുതാം. അതല്ല എങ്കിൽ നോർമൽ കേസിൽ നമുക്ക് mu 0 I by 2 pi A എന്ന് എഴുതാൻ പറ്റും. ഇനി ചില കേസുകളിൽ നമുക്കൊരു പക്ഷേ മാഗ്നറ്റിക് ഫീൽഡ് ഇൻറ്റൻസിറ്റി കണ്ടക്ടറിൻ്റെ ഒരു എൻഡിലാണ് കണ്ടുപിടിക്കുന്നതെങ്കിൽ phi 1 എന്നുള്ള ആംഗിൾ 90 ആയിട്ട് വരും. ഇത് റെഫറൻസ് ലൈൻ ആയതുകൊണ്ട് phi 2 എന്നുള്ള ആംഗിൾ 180 ഡിഗ്രി ആയിട്ട് വരും. അപ്പോഴാണ് നമ്മുടെ ഇക്വേഷൻ mu 0 I by 4 pi A into sin 90 പ്ലസ് sin 180 വരും. ഇത് 1 വരും, ഇത് 0 വരും. അപ്പോഴും നമ്മുടെ ഇക്വേഷൻ B is equal to mu 0 I by 4 pi A എന്നായിട്ട് മാറും. അത് വളരെ ഇമ്പോർട്ടൻ്റ് ആയിട്ടുള്ള രണ്ട് പോയിൻറ്റ്സ് ആണ്. നമുക്ക് തന്നിരിക്കുന്ന മാഗ്നറ്റിക് ഫീൽഡ് കാണുന്നത് ഈ ഇൻഫിനിറ്റ് കണ്ടക്ടറിൻ്റെ സെൻട്രലായിട്ടാണ് നമ്മൾ ഉപയോഗിക്കുന്നതെങ്കിൽ നമ്മുടെ ഇക്വേഷൻ mu 0 by 4 pi into 2I by A എന്നോ mu 0 I by 2 pi A എന്നോ എടുക്കണം. അതല്ല ആ പോയിന്റിൽ ഫ്ലക്സ് കാണുന്നത് ഈ കണ്ടക്റ്റിംഗ് സിസ്റ്റത്തിൻ്റെ ഒരു എൻഡിലാണെങ്കിൽ നമ്മുടെ ഇക്വേഷൻ mu 0 I by 4 pi A വരും. mu 0 I by 2 pi Aക്ക് വരാം, mu 0 I by 4 pi A എന്നായിരിക്കും നമുക്കിത് വരുന്നത്. ഓക്കെ.